Hi there, my name is Zahid Haq, and this is my presentation on ATP Pathways for KIN 516 Advanced Exercise Physiology. So here is the breakdown on how our bodies produce energy or adenosine triphosphate during exercise using two different pathways, the anaerobic and the aerobic. First, we have the anaerobic pathway, which doesn't require oxygen. In this process, the glucose is broken down into the pyruvate, and when there's no oxygen available, the pyruvate goes through fermentation. This produces either ethanol or lactic acid, depending on the situation, and creates a quick burst of energy in the form of 2 ATP molecules for each glucose. This pathway is fast, but not very efficient, and typically used for short, intense activities like sprinting, weightlifting, powerlifting, gymnastics, and wrestling. Then we have the aerobic pathway, which uses oxygen. Here, glucose is also broken down into pyruvate, but this time the pyruvate enters the mitochondria, and this is the energy powerhouse of the cell. Once inside, it goes through the citric acid cycle, and then the electron transport chain, or the ETC, uses oxygen to produce a lot more ATP. In fact, the aerobic pathway can produce up to 30 to 32 ATP per glucose molecule, which is much more efficient, but it takes a lot longer. To sum it up, in aerobic processes, you can get a quick 2 ATP while in aerobic processes, and you can generate 30 to 32 ATP. And that's why your body uses the anaerobic system for short, intense efforts, and the aerobic system for longer, sustained activity, such as playing soccer, boxing, MMA sports, and any high-intense interval training. As we take a look at this graph, it shows our body energy systems change during exercise. In the beginning, the anaerobic processes, which don't need oxygen, they're working hard to supply almost all of the energy for the first minute or so. And this is the yellow line on the graph here. But as the exercise continues, the body can't keep relying on this fast energy source. So by the second minute, it starts to decline, and after about 3 minutes, it's barely contributing. So meanwhile, the aerobic processes, which do need oxygen, start slowly at first, and as you can see by the red line, it does go up after about a minute, and they quickly start to, which is when they quickly start to kick in. By the time you reach round 2 or the third minute into the exercise, the aerobic system takes over as the main energy source. By 5 minutes, it's almost entirely responsible for supplying the energy. The key takeaway here is that our body shifts from quick anaerobic energy system to the more efficient, long-lasting aerobic system as exercise goes on. Again, examples being boxing, UFC and MMA fighters, soccer players, basketball players, etc. This shows how important oxygen and aerobic metabolism are for sustaining longer activities. Now, if we want to talk about the limits or the limitations for the production of energy or ATP in our bodies during exercise, we need to first look at the anaerobic pathway, which doesn't use oxygen. It's limited because it produces lactic acid. As this lactic acid builds up, it leads to muscle fatigue, making it harder to keep going. And you'll see this if you power lift or strength training at the gym, trying to get past 20 reps at obviously using the correct weight is, you're fatiguing the muscle, and this is a great example of where the lactic acid starts building up. Plus, the anaerobic ATP production is pretty efficient and doesn't provide as much energy as the aerobic system. For the aerobic pathway, which does use oxygen, the main limitation is the availability of oxygen itself. If your body can't get enough oxygen, it can't keep producing energy efficiently. Additionally, the performance of your mitochondria, where the aerobic energy is made, and how well the electron transport chain works, also play a big role in how much ATP can be produced. A side note to this is Real Madrid, the football team from Spain, to combat this, all the players actually use Vicks, which is a menthol supplement, which they rub onto their chest and under the nose to open up the gateways in the nose to be able to breathe more oxygen and obviously play longer and more efficiently. And I know like football and soccer or soccer science is heavily looking at ways that these players can play on longer for longer minutes without being exhausted. In short, anaerobic energy is limited by lactic acid buildup, and aerobic energy depends on oxygen and how efficiently our cells can produce ATP. So if you look at the real world and how these energy systems work, for high intensity activities like sprinting, lifting weights, the anaerobic pathway steps in. It gives you a quick burst. It gives you quick bursts of energy because it can produce ATP fast. However, for longer, moderate intensity exercises like running or cycling, the aerobic pathway takes over, providing a steady supply of energy for a longer time. When we exercise, both systems are important. The anaerobic pathway kicks in first when your body needs energy quickly, but as you keep going, the aerobic pathway takes over to provide the sustained energy. While we can't rely on just one system, the anaerobic system shows that it is fast but inefficient and can lead to fatigue, while the aerobic system is efficient and long-lasting but takes more time to get going. That's why the balance is key. Different types of exercise need different energy systems to help you perform at your best. Now, in regards to how the fat cells and how they affect the ATP, our bodies use ATP as the main energy source for like activities, as explained previously. We produce ATP through three gateways, and that's glycolysis, the citric acid cycle, and the electron transport chain. First, glycolysis breaks down glucose and gives us 2 ATP molecules. Then the citric acid cycle follows, producing 2 more ATP indirectly. And finally, the ETC is where the real energy comes in, making between 28 to 34 ATP for molecules like NADH and FADH2. Overall, glucose and fats, such as palmitate, fuel these pathways, helping us to stay energized for everything we do. The glycolysis is a process where glucose is broken down into the pyruvate, and it can happen both with or without oxygen. This takes place in the cytosol of our cells. The glycolysis gives us a net yield of 2 ATPase and 2 NADH, which can provide about 5 more ATP in aerobic conditions. However, if there isn't enough oxygen, the NADH cannot be fully used in the ETC, and we may experience a buildup of lactate. This process is particularly important during high-intense, short-duration activities like sprinting, where fast-twitch muscle fibers rely heavily on glycolysis for quick energy. Studies do show that glycolysis plays a dominant role in these activities. The citric acid cycle, also known as the Krebs cycle, is a key part of how our bodies generate energy. It starts when the acetyl-CoA enters the cycle and is oxidized, producing NADH and FADH2, which are used to fuel the electron transport chain. This process happens in the mitochondrial matrix. The citric acid cycle yields 2 GTP, which is equivalent to 2 ATP, along with 6 NADH and 2 FADH2, giving a total of around 18 more ATP. This cycle is especially important during moderate intensity, long duration like jogging, where it keeps producing energy efficiently. Research also shows that this aerobic pathway is more active in slow twitch muscle fibers during longer, steady activities. The electron transport chain, or ETC, plays a vital role in energy production within our cells. It uses NADH and FADH2, which are generated from earlier metabolic pathways to produce ATP through oxidative phosphorylation. This process occurs on the inner mitochondrial membrane and is responsible for yielding 2.0 ATP per NADH and 1.5 ATP per FADH2, which contributes to a total of ATP production of 28 to 34 ADP molecules from glucose oxidation. A key factor in the ETC is oxygen, which serves as the final electron acceptor. So without sufficient oxygen, this process cannot function efficiently. The mitochondrial health and efficiency are also crucial for the optimal ATP production. In the context of exercise, the ETC is more efficient during low intensity prolonged activities such as endurance sports. And research has also shown that endurance training enhances mitochondrial biogenesis, which improves the capacity of the electron transport chain, which boosts overall energy production. Understanding and supporting the health of the ETC is key for optimizing performance, particularly in endurance athletes. So our bodies utilize different energy pathways depending on the intensity and duration of the exercise. During high intensity, short duration activities like sprinting, anaerobic glycolysis takes the lead, providing quick ATP but in limited amounts. For moderate, intermediate, or moderate intensity long duration activities, like jogging, a combination of glycolysis, the Krebs cycle, and the ETC work together to produce a higher and sustained ATP yield. In low intensity, prolonged activities such as endurance sports, the ETC becomes the primary energy source, using fats for a slower but larger ATP production. Research shows that the different substrates are preferred based on exercise intensity, carbohydrates for short bursts, and fat for endurance activities. Each energy pathway from glycolysis to ETC have limiting factors. For example, anaerobic glycolysis is limited by lactate buildup, while aerobic pathways are dependent on oxygen availability and mitochondrial health. In real-world applications, quick ATP from anaerobic glycolysis is essential for high-intensity efforts, but longer sustained activities rely on aerobic systems like the Krebs cycle and ETC for efficient energy production. You can't rely on just one system because oxygen supply and substrate availability vary by exercise type. So in conclusion, understanding how these pathways integrate is essential for optimizing training programs, whether for endurance or power-based activities. And that's it for my presentation. I do appreciate your time that you've taken to follow my presentation, and that's it. Thank you very much.